Hey, welcome back, class. In previous lessons, we've looked at how to draw Lewis structures and then to take a look at the geometry of that Lewis structure to determine, whether or not it has like a tetrahedral or a linear form, just to name a couple of examples. So, in this lesson, I want to sort of expand upon that and let's take a look at the concept of polarity. So whether or not something is polar or nonpolar. And so we need to remember from other lessons that polar or nonpolar. A pole, remember, is just a side, right? So remember we said a pole equals like the side or an end. And so if we're looking at whether or not a molecule is polar or nonpolar, we're looking at is one side or end or multiple sides or end of the molecule, or it could be an ion. But typically right now we're just looking at, because ions carry a charge, obviously. Then we're just wanting to know the molecule itself, does it have some asymmetry to it, or some symmetry to it, which would determine if it's polar or nonpolar. So let's just two kind of classic examples here: carbon dioxide and chloroform. We'll just start with CO2 because we're all very familiar with that molecule. So we got carbon dioxide. And from previous lessons, we know that we've got carbon dioxide. It's double bonded to oxygen in a very linear form, right? And so remember that those lone pairs, they're off at angles. And so that's a previous lesson. If you forget that, you're going to want to go back and take a look. What we need is to evaluate what's going on with the electronegativity values for each of the atoms, the way they're bonded. So electronegativity is this concept where there's this constant push and pull. So this carbon is pushing on this oxygen here, and it's also pushing on this oxygen here, because the electrons on the outside, they're repelling each other. So all these electrons on the outside of the atoms are repelling each other. But at the same time, even though I've just said this carbon is pushing on oxygen, we can also talk about this as the oxygen is pulling on the carbon. And this oxygen here is also pulling on this carbon. Because remember that at the heart, essentially, of all these atoms is a positive nuclear core. So that positive nuclear core has an ability to attract those negative parts of not only the electrons on itself, but also the electrons around it that are also part of another atom, which is where covalent bonding comes in. That's all right. So that means that also this carbon is pulling this oxygen this way, and this oxygen is pulling this oxygen this way. Now, whether or not it was single or double bonded, this would be the case regardless. We just happen to have a double bond between both of these atoms, right? So another way we could think about this is this carbon to this oxygen, that oxygen is pulling carbon towards it, and carbon is pulling oxygen back towards it. And the same is true for this oxygen over here. Carbon's being pulled by this oxygen, but carbon is also pulling this oxygen this way. And there's this constant back and forth, back and forth, back and forth. So molecules they're sort of they're vibrating, they're moving. They're not just static pieces that are physically connected. They're constantly moving around each other and pushing and pulling and stuff. So that's what you need to try to visualize. Okay. So now with that said, we need something else. So there's this thing, this electronegativity scale, that if you're in my class, you have a copy of this. And you can find this in various places, and depending on where you go, depending on which text or resource you look up, you may find these electronegativity values where you have they go to the nearest hundredth place instead of just the tenth place. So this is a nice, neat, and orderly one that we like using for class. And I've got these notes right down here for you. All right. So typically, if a bond between two atoms is basically 0.3 or less, it's being identified as nonpolar. There's really not much of a pull, more so in one direction. It's pretty evenly dispersed. We're going to say it's nonpolar. Conversely, if it's much higher than that, we start calling it a polar. We start saying that it's very polar. In other words, more towards one side or end is the pull between the atoms, and so we would see more of an asymmetry. And then this last thing that we have here, 2.0 or greater, being ionic. And now sometimes, with that said, you can get things that are like 1.8, 1.9. Though that's less than 2. It's close to 2, but it is still less than 2. And and it could exhibit some partial partial covalent polar properties. All right. So I just wanted to bring your attention to that. So now what you do is you take a look at this, and depending on the atom, you literally just take the numbers that you're working with for those atoms. Well, right now we're dealing with carbon dioxide, so we need this 2.5 and this 3.5. We need those two numbers to help us figure this out. So let me go ahead and erase that. Let's go back to where we were on this. So carbon, we said, was 2.5 for an electronegativity value, and oxygen was the 3.5, right? 3.5. So remember, you're just always using the numbers here, and you're using those numbers there. Okay? So now what you do is you evaluate one region of space at a time. So we're going to just evaluate what's happening right here in this region of space first. All right? I just picked the left side just to pick it. So 2.5 to 3.5, think of this as a tug-of-war contest. There would be a greater pull towards the oxygen here overall, which, if you were to try to envision it, that means that the electrons that are here and here are actually being pulled a little bit more in this direction than they are the carbon. And all these electrons, the electrons that are here and here, are also being pulled a little more in this direction. And so the density of electrons is actually more so on this side of this carbon-oxygen double bond. All right. So what we do is we call this right here, we say that now this side of it here is more positive, which means less negative. And the difference is 1.0. I'm going to go ahead and put that in parentheses just so we can differentiate. And what I just drew was what we call a dipole moment, right? And hopefully, we've talked about this before, but that means two, and that means size. So two sides. Moment means like right, kind of at that moment of time, during that period of time of interaction at that moment, right? So there is a 1.0 in that direction right there. That's our dipole moment. That arrow with the positive symbol, that's how we represent a dipole moment. And we can see that the same is happening in this direction. That's also 1.0. Now you have to envision this like there's 0. You have to envision this as like a tug-of-war contest, right? And to what we look at as to our right when we're looking at something, or to our left, we see as positive or negative respectively. We have to think of this as a tug-of-war contest right here, like there's a flag right here. And we see that there's a positive 1.0, and then there's basically a negative 1.0. And if you add those two together, they basically cancel each other out. And so what we see happening in this situation here is there is no net pull right or left, so to speak, on this molecule to one side or the other. So we would say that there is no net dipole moment, all right? The net being the overall effect, not each individual one, but the overall effect on the molecule itself, all right? If there's no net dipole moment, we would say that this is exhibiting an asymmetrical form. It has asymmetry to it, all right? Oh, I'm sorry. I misspoke on that. I apologize for that. It is being pulled evenly on both sides. That is symmetrical. I apologize for that. It is symmetrical. All right. So we can see if you've got 1.0 towards one side, 1.0 to the other, the pulls are basically even. So the electrons would be fairly evenly dispersed on both sides of this molecule, so to speak, right? So no net dipole moment. It's symmetrical. If that's the case, then there's not one side more negative or positive than the other. We would say that this is a non-polar molecule, because each of those bonds are polar, but the overall effect is that the whole molecule is symmetrical, so it is a non-polar molecule. All right. So now let's take a look at our chloroform. All right, let me get that out of the way for you. So chloroform, CHCl3. All right, if we were to draw a structure for this, carbon at the center, we have hydrogen, and then there's chlorine, chlorine, chlorine. Remember, we've got these lone pairs here that are needed, and now there's our chlorine molecule. And this has a tetrahedral geometry. Remember, there's 1, 2, 3, 4 domains around that, of electron domains around that central atom. 4 domains. This is going to have a tetrahedral geometry to it. And so when that's the case, we know what we have to do is draw a 3D Vesper structure. And so we have to use our wedge and dash to exhibit that, right? So I'm going to go ahead and put that hydrogen up here, put that chlorine, put the chlorine, and put the chlorine is off to the side there. And remember, when we use wedge and dash on any atoms that connect to the central atom, we do not put the lone pairs there. We know they're there. We assume they're there. The whole purpose is to take a look at the angles that exist around that central atom. That's the important part for the wedge and the dash. All right. Now the lone pairs are contributing to how far apart the chlorines and everything are, but that's a completely different lesson and a different topic. All right. So let's get rid of that. So let's go back to our electronegativity scale. We can see carbon, right? Carbon has 2.5. Chlorine is 3.0. And then we can see over here, hydrogen 2.1. All right, so we've got 2.1 for hydrogen. So I'm going to go ahead and put a 2.1 here. Carbon we saw was 2.5. I'm going to go ahead and just put 2.5 here. I could put it on the other side. That'd be perfectly fine. And then the chlorine, we can see chlorine is 3.0. So I'm going to put 3.0 here, 3.0 here, and I'm going to put 3.0 here. Now, one at a time, you want to evaluate each covalent bond. So I'll just start here at this one, and then we'll work our way around. All right? Why not? I'll just start at one and Decided to go counterclockwise. Why not? All right. So we can see that 2.5 has a greater pull towards 3.0, right? And the difference there we see is 0.5. We can see here on this chlorine, or this carbon to this chlorine, there's a dipole moment as well. And that is also 0.5. I'm going to put that net difference value in it, the magnitude in parentheses there. And then from this carbon to this chlorine is also 0.5. And you'll notice that I try to draw all the arrows the exact same length. That is a detail you want to try to pay attention to. If possible, if you have to, you draw your structure a little bit bigger to make room for that, because this is a mathematical concept. So go back to what you remember from your math teachers. If you're drawing out like XY coordinates, if you have something like, or go back to geometry, if you have a ray, right? So you've got something like this, then by definition, you would say that this one right here that I just drew has greater magnitude than the one above it because it has greater length. All right, and so you're going to want to keep in mind that we're using these sort of standards that you've been taught. All right, we're just using them here. All right, they just go across the disciplines of math and science. Now we have the carbon-hydrogen bond and 2.1 and 2.5. Well, we can see that 2.5 is greater, so there's a greater pull from this hydrogen to that carbon, or the carbon is pulling it, right? So the hydrogen doesn't have as much of a pull. The carbon has a greater pull. And the difference there you see is 0.4. Okay, so if we look at this, let's think about this for a second. All right, let's think about this for a second. I'm going to draw carbon tetrachloride. If we had carbon tetrachloride, all right, carbon tetrachloride. Who cares what the numbers for chlorine are? But let's go ahead and take a look. So chlorine, remember, over there, remember, is 3, right? So we've got 3.0 here, 3.0 here, 3.0 here, and 3.0 here. So carbon was the 2.5, so there's a greater dipole in this direction, this direction, this direction, and this direction. So, and they all are of equal value. They would all be 0.5, all going out in 4 equal directions from the center. So imagine you are the carbon atom, and you're being pulled in 4 completely different yet equal directions. No matter which way you look, you have to imagine that each of these angles right here, they're all the same. No matter how you rotate this, remember this is a 3-dimensional thing, they're all the same. So if this is you right here in the center and 4 people were evenly spread out around you and were pulling on you, you would not go in any one direction because everything is being pulled equally. Now imagine that all of a sudden the person who's right here, imagine that they are not pulling quite as much. You can already see that from where you are here in the center that you would probably start moving in that direction. Just a little bit, ever so much. And the same is true with this molecule here. There is a pull slightly through that part of the molecule. And we would call this, we would say that this side going in this direction is partially negative, and we say this side is partially positive. All right. So now what happens when you have this? I'm going to get let me get this out of the way for you. Now what you do is you come parallel to your net dipole. And if you remember from your math teachers, you can move axes parallel to each other and they still have the same value, right? And so this would be our partially negative, our partially positive side or end. All right, so this is our net dipole, right? And so we can see here that this thing it's partially polar. We would call this a partially polar molecule. It doesn't have a huge pull, but there is a little bit of a pull because of that slight difference, because those chlorines are pulling a lot more than what the hydrogen is. So you could almost think of it this way, that two of these chlorines kind of cancel out. All right, they kind of cancel each other out, and then what happens is now you're looking at the interaction between here, here, and here. And so technically you would kind of see more of a pull kind of at an angle like this through it, leaning towards two of those, and it's constantly kind of moving back and forth, but it's going through there. Okay. All right. I hope that helps a little bit. All right. We would say something like this is partially polar. All right. I hope that helps. So now you've seen polar, you've seen nonpolar. It's all about looking at the electronegativity values and determining if there is a net dipole. If there is a net dipole, then you would have asymmetry. So we would say that this molecule has asymmetry. It is asymmetrical. All right, because it has a net dipole moment. Check. All right, and there's an electronegativity difference in that net dipole, which is causing it to move in that particular direction. All right. Hope that helped. Take notes, rewind, pause, look back at this, work on those problem sets that I have for you, check your answers, etc. Reach out to me if you need help. Always great learning with you. Take care. Stay curious. I will see you in another lesson real soon. Bye.